All right, ready? All right. So welcome everybody here and everybody out on the web. Thank you for joining us. This is the last of the TCIPG seminars for 2011. We will resume again in 2012. Details to follow if you're on our mailing list, of course, as to topics and dates. I'm Al Valdez, for those of you who don't know me. I'm, well, I guess I can't say recent because I've been here a few months now, but I'm Managing Director of Smart Grid Activities at University of Illinois. And I'm here to introduce our speaker, Dr. Mischa Steurer. He's going to be talking about the overview of hardware and the loop simulation capabilities at the Florida State University Center for Advanced Power Systems. That's CAPS, the acronym CAPS. He's using, talking about using commercial tools such as RTDS and OPAL-RT. And of course, some of the TCIPG institutions have RTDS capability, although probably somewhat limited by comparison. He'll talk about some example hardware and loop simulation projects, international activities, and present some future directions. Our speaker holds a bachelor's and a master's from the Technical University in Vienna and a doctorate from the Swiss Federal Institute of Technology, and all of these are in electrical engineering. He is currently a scholar scientist at CAPS, leading the power system group, focusing on hardware in the loop simulation, modeling for all electric ships, as well as future terrestrial power systems. Some of his other interests are clued improvement, maybe he'll tell us exactly what that is, of the integration of novel high-power apparatus such as superconducting devices, power electronic converters, and novel rotating machines into power systems. He has over 100 technical papers, numerous best paper awards, and some patents. Member of IEEE and SIGRA, is that how and he chairs the IEEE working group on testing fault current limiters, in addition to major contributions to a number of other IEEE and SIGRA groups. He's the testbed leader for the FREEDM Center that many of you have heard about. This the first three letters are Future Renewable Energy. I'm not sure what maybe he'll tell us what it is. He has said that he is willing to take questions during the talk. If you have a question, usually we do a question-answer session afterwards. If you're on the web, you can submit questions via web chat. And with that, I'll turn it over to the speaker.
Thank you very much. Okay, let's see if this works. Yeah, looks like I'm unmuted now. Thank you very much, and thanks for inviting me to this occasion here to give the lecture and the seminar. As the title says, I'm going to talk about our hardware in the loop simulations at Florida State University Center for Advanced Power Systems. And I've been there since 2001, when the center was essentially just getting off its feet. I'll talk a little bit about that. And here you can reach me at my email and phone number. So the outline of the talk is such that I will give you a very brief overview of CAPS, just to give you the background and what are we doing in a large scheme of things. And then jump right into hardware in the loop, short agile concepts and challenges. I'll talk briefly about real-time simulators, give you an introduction to that, touch upon interfaces that between the real world and the simulated world as it pertains to some of the challenges that one faces when one performs those real-time hardware in the loop simulations. And I give a bunch of examples of project that we had in the past and currently ongoing to give you a flavor of what we're doing and the space in which we work with. And then I briefly touch upon CAPS facility expansions and some concluding remarks. And as I said, if you have an emerging question that you can't hold, then please just raise your hand. I'm more than happy to entertain the questions right away. Oops, well, okay. So this is the one overview slide of CAPS as far as our broader concept goes. This is our building at the lower left corner. We occupy pretty much the first floor of that building, which sits in Innovation Park in Tallahassee, next to the National High Magnetic Field Laboratory. It's an NSF-funded national laboratory that provides magnetic field, very constant values for experiments in the physics world and so forth. And we grew out of the magnet lab as a small core of people that realized that a center like that is very helpful and useful. So we occupy the first floor. You see a high bay testing building facility back there, and pretty much the half of the second floor and pretty much the third floor is ours. So that building is more or less ours right now. We were established in 2000 with a seed grant from the Office of Naval Research. The Navy has realized that power systems research is important to them for their all-electric ship program. And meanwhile, we are the lead institution for the ONR funded Electric Ship Research and Development Consortium. That's ESRDC for short. We focus on research and education related to the application of technologies in the electric power systems in a broad sense. And we have roughly about an $8 million annual research funding from ONR, DOE primarily, and then industry funding. And we have a DoD cleared facility at the secret level to perform classified work, which we currently don't have a classified project, but we have all the measures in place to do that if necessary. The research focuses on various different aspects of power systems, advanced modeling and simulation. That's where I work in a lot of times. Advanced control systems such as distributed control, agent-based control systems, power electronics integrations and controls, so photovoltaic converters, how they interact with the grid, developing new topologies for more compact power electronic devices. We have a thermal management group, and there's also, because of the vicinity to the National High Magnetic Field Lab, there is a high temperature superconductivity group. And when you deal with high temperature superconductivity for power applications, it comes naturally that you have an electric insulation and dielectrics labs that specializes in cryodielectrics. So how do you make insulation system that shield and provide dielectric insulation in the cryogenic environment at low temperatures? This is the size of the laboratories, and we have about $25 million in specialized power and simulation equipment invested by DOE and ONR, and currently about 100 people. Half of them are scientists and engineers like myself, working currently at the lab permanently, and then we have joint affiliations with FAMU, FSU College of Engineering faculty, and we're about 44 students, or roughly 50 students typically working at the center. Here is the organizational structure. We are directly under the Vice President of Research. Okay, we have a director, we have an associate director, and we have these focus groups where I lead the power system group. All the names up here are either faculty or postdocs or permanent staff. They don't list the students here. And then we have a large group that runs the facilities and the simulator support. These are all, technicians and specialists working in the power lab, and you will see why we need such a staff, because we have a pretty extensive power laboratory capability. So to wrap up the broad overview of the center itself, here are some major collaborative research efforts. Primarily, of course, the ESRDC, the Electric Ship Research and Development Consortium. Florida State is the lead, Mississippi State, University of South Carolina, University of Texas and Austin, MIT, Purdue, and the Naval Academy, and the postgraduate school are all in this consortium, work together on all electric ship-related power systems and controls and thermal management questions. There's a State of Florida initiative of all the universities in Florida, which that initiative is essentially currently at the in the last year of its activity, FESC, the Florida Energy System and Systems Consortium. We're also part of the FREEDM. Here is how it's spelled, what it means: Future Renewable Electrical Energy Delivery and Management Systems, FREEDM without an O. It's NSF funded, NC State is the lead, and we are partner university here. And then we have a DOE grant that we dubbed SunGreen, the Sunshine State Solar Grid Initiative, that deals with high penetration of PV in the state of Florida. So what are the integration issues? How do you model these things? And how can you make, from a technical point of view, how can you increase the penetration level of PV in the state of Florida? And there's a bunch of utilities and other, USF, for example, University of Central Florida is in the South Florida, sorry, is part of that, and several others, utilities and providers of PV converters and so forth. So these are the big consortia, and the rest is individual grants and projects that we deal with on an individual basis. So now let me jump right into what about the testing part of it and the laboratory activities that we use the Power Lab for. There is a need for early stage prototype testing at the power level that goes beyond building a widget and hooking it up to the grid and perform maybe a few limited tests for short circuit tests and things like that, because the onset of the power electronic world, where now we are dealing with a lot more power electronic devices, PV converters in the terrestrial world, motor drives and DC-DC converters and so forth in the advanced power systems world on ships. These devices have substantially more controllability, and therefore may and will it may be possible to use them for much higher control capabilities in the grid, and dynamic interactions between those devices is essential to understand properly. So the facilities that you will see during my talk are basically designed and aimed at developing appropriate models and validate those models of those pieces of equipment that go into the service in various grid configurations, be microgrid or being a ship system, to allow early stage studies of a design incorporating the dynamic interactions between those pieces of equipment. And it is clear that some of these advanced and elaborate testing capabilities are very difficult to facilitate in classical settings, where you basically either build a mock-up of an entire system. It is costly to build that. It is very inflexible to change parameters, and the number of scenarios that you can actually run in that large settings are limited. So we have come up with some new ideas and possibilities using the so-called power hardened loop simulation. I will elaborate on that. So this is sort of the introduction to the motivation of why we're going that route. So let me give a few definitions. We deal with controller hardware in the loop, what we dub CHIL, and power hardware in the loop, PHIL. The major difference is that controller hardware in the loop simulations, you have a simulation piece that the simulation executes in real time, and I will quickly touch upon what that means, interacting with a controller device or a protection relay. Something that, a microcontroller that has to control a piece of power hardware, for example. And typically it exchanges low-level signals at the plus minus 15 volt level, couple milliamps, with the simulated piece of the rest of the system. So the interfaces are really primarily A to D converters, or in some cases direct digital communication channels. Whereas the power hardware in the loop simulation requires a power interface to scale the signals that come from the simulator up to a decent power level, so you can connect a piece of power hardware at, say, 4.16 kV, that's a typical distribution class voltage, to the simulated rest of the system. And vice versa, then signals measured from the response of the device have to be translated back from high power and high voltage and high current values back into the simulated world, that is, on the digital world. So this power interface here is really a challenge, because in many cases this power interface will introduce additional delays and inaccuracies that can significantly impact the overall power hardened loop simulation. The overall goal is that this device on the test completely transparently being connected to the simulated world, whereas the simulator sees the power device being interacting with the simulated world and you can completely study that interaction. So what we have in Tallahassee at FSU CAPS this is the background view from the building that you saw before on the picture. So we have a high bay testing building. You see in the foreground a 2.5 megawatt cooling tower that can reject up to 2.5 megawatts of heat. All these power electronic devices have to be cooled. So if you talk about megawatt scale capabilities, you need that. And most recently we had a high bay build. So this is about 9 months old, that picture. So right now this is populated with other high power equipment. But most of the activities as far as the high power test facility is concerned is going on here, and the simulator, the RTDS simulation lab is right up here. Inside we've got a bunch of power hardware, transformers and switchgear and variable speed drives and dynamometers for testing rotating machinery. And we'll explain a little bit about that and give you a few examples on what we've did in the past. These dynamometers here are capable of jointly providing 5 megawatt at 225 RPM at the shaft coming out there, and you can connect a rotating machinery here. Overall, the power facility is rated at 7.5 MVA with the flexible AC and DC sources at 5 megawatt. And hopefully you will learn more when I go through this rest of this presentation. So here's a little diving into the single line diagram of the facility with regard to the electrical power hot-water loop capabilities. As I said, the idea is to run a rest of the system simulation on the real-time digital simulator, or RTDS, which is our workhorse for the real-time simulation. And you see our 14 racks of RTDS in the lab here. Within the foreground, there's a rack of relays and some other substation automation equipment. So the rest of the system is simulated here, and this is a 5 megawatt back-to-back converter system, which really, this is the picture of what you see here. We come off the 4.16 kV internal distribution into a active rectifier system, which on its output side allows us to generate voltage waveforms as they've been simulated in real time by the simulator. So it's really an amplifier system for our real-time simulator. And then we have various configuration capabilities. In AC mode, we can go up to 6.25 MVA at 4.16 kV, where we completely control the waveform on that bus and connect pieces of hardware to it. We can step that down to up to 480 volts for low voltage equipment. And we have half of that system is configurable to become a DC source or sink, which allows us to do experiments up to 2.5 megawatt at a kilovolt level in the DC regime. The bandwidth, the usable bandwidth of this amplifier converter is about 1.2 kilohertz, as it is switching at 10 kilohertz. So it's I don't know how familiar you are with power electronic converters, but you're basically using power switches, semiconductor switches, to basically chop up waveforms, so you can reassemble waveforms by turning on and off a switch that connects the output of this device to a DC link, a constant voltage source, and by changing the duty cycle, you can basically modulate sine waves or other waveforms that come out of the simulator. And by having this relatively high switching frequency for a power rating of 5 megawatt, we are able to utilize a bandwidth up to 1.2 kilohertz. So we can reproduce unbalanced voltage waveforms. We can introduce harmonics and so forth, frequency deviations and the like. Overall, okay, there's a question.
Can you go back? What type of the bottom one, the last one? What type it is?
Hold on for a second.
Type is the last one.
Yeah, okay.
There is the AC.
This one?
There is the DC, yeah.
Yeah.
What about the experimental?
Okay, so this converter system is comprised of two sets of converters. They are completely independent, really. Two independent converter strings that both pull power from our utility feed. but can be controlled independently on the output. So I either use them in tandem when the switch is in this position, in tandem to provide 6.25 megawatt at this bus where I control the waveform, or I switch this over to the DC side, leave this transformer alone. I have half the capacity on this bus, still AC, and I have half the capacity more or less on the DC side. Now, and you will see at the later slide, you can actually connect a power device between those two buses. For example, a photovoltaic inverter that on the one hand believes it's connected to a photovoltaic array, and on the other side it's connected to a 480 volt utility bus, yet the device is completely isolated from a real PV array or from a real utility bus because we are simulating both sides. Okay, so that's the idea. This device essentially acts as an amplifier to the signals that come out of the real-time simulator. Did that answer your question? So overall, it's just a little different rendering of the overall testbed configuration. In the core, we have the real-time simulator where we can essentially simulate relatively large power systems. We have connections to control and protection devices such as relays and a commercial OSI Pi EMS system that we have integrated here to a reasonably large extent. This is still in progress here. The real-time simulator also connects seamlessly with the power test facility, and that's the real novelty, because you can now basically operate a 5 megawatt power test facility from a digital real-time simulator. And that's really, we've certainly spearheaded that. And as you can see in one of the last slides, other folks are starting to pick up on that and are following our lead. So that's really, in a nutshell, the capabilities. We also have cryo capabilities. Don't want to touch too much on this, but the superconductivity regime, the superconductivity group, of course, needs cryo cooling capacity and needs the cryodielectric labs, as I said before. Okay, so real-time computer simulations. Okay, what does that really mean? Well, it simply means that the simulation must be we talk about time domain simulation. So we talk about simulating the behavior of a system into time domain. The real-time simulators utilize pretty much the same or similar algorithms that non-real-time simulators do. However, they are tailored such that the models execute fast enough such that when you have a sequence of events, that you don't run into overruns and you don't run into longer computational times that each time step requires to keep in sync with the time. So the real-time simulator executes their respective code per each time step faster than the interrupt times that you typically see. 50 microseconds for power systems is a typical scale here. And so by the time you ought to have the solution according to the wall clock, you already have it. And there is no overrun. Which means some of the algorithms that are used in non-real-time simulations that use iterations, for example, are no good for real-time simulation. So you have to acknowledge the fact that you have to get done with the one time step evaluation of the entire system, all the equations that govern the system within that 50 microseconds or whatever your scan time of the simulation is. And the purpose of that is, of course, to provide a simulated environment to a piece of hardware that now the piece of hardware believes that what is simulated is actually the real system, and it can interact with it. Okay. So keep that in mind, that this is one of the challenges. So sometimes when you build models on some real-time simulators, you have to acknowledge the fact there is no iteration. There is no stepping back and reiterate until you find a solution and walk on. In most cases, now there are some limited capabilities that you can utilize, because you never know how long that's going to take. And if you don't know how long it's going to take, you cannot guarantee that the solution is done by the time it has to be done to provide that to the real piece of hardware. So, in the past, this is how a real-time simulator has looked like. Okay? This is a transient network simulator, analog version, courtesy of BPA at Celilo, at the HVDC center, at the HVDC pole at the north end of the Pacific DC intertie, that essentially models the Pacific DC intertie, part of that, and the control system is embedded in here. Why they use that? Because the Pacific DC intertie ships, 3,000 megawatts of power on a good day, and in order to make sure that all the protection, all the controls work, you cannot play around with the real system too much. So you use a device like that. Now imagine you want to reconfigure this, and you've got all these wires and all these connections. Okay, this, by the way, is a way to represent rotating machinery. This is a true, real motor. Actually, I think this is a synchronous condenser model. They still operate this, but all that can be dumped onto a real-time digital simulator where you don't have all these wires. Okay, you still can connect to the control piece of it. That's the whole purpose. But you save yourself a lot of grief if you can get away with a digital version of that. You can also port the models. Maintenance is easier, and it's much more user-friendly. So that's the reason why RTDS has actually embarked on starting the company and building it, and we're so successful in selling it. So that's just an anecdote here. I thought that you would appreciate the differences here. This is again our little slide here, just summarizing what the RTDS basically provides you with. We have 14 racks of RTDS at CAPS. It uses the classical EMTP, electromagnetic transient program algorithm. Herman Dammel had developed that in the 60s, 70s to simulate large grids, large power grids, yet in the transient time domain. And it essentially uses that algorithm. It can go down to time steps roughly of 2 microseconds for power electronic subsystems. Not the entire simulation, not an entire system is simulated at 2 microseconds, but power electronic subsystems are possible to simulate at 2 microseconds with a higher fidelity, so to accommodate switching frequencies of power electronic converters up to typically 5 to 6 kilohertz, which is currently state-of-the-art for high-power electronic converters. I mean, you will find much higher switching frequencies in an electric vehicle, so that those switching frequencies cannot be accommodated. But for a StatCom, a static var compensator, or other back-to-back HVDC systems or so forth, these timescales are currently okay. It interfaces through analog interfaces to equipment, and also with digital capabilities, Modbus, TCP, DMP3, IEC 61850 are all available, and you guys have a rack here with that capability. Of course, we use other tools as well at CAPS. It's not our own, not our only simulation tool, but it's certainly the preferred real-time simulation tool. We also have this box here. This is a Opal RT system, and the Opal RT system is clustered, where the RTDS is using proprietary hardware and software. Opal RT system is really is centered around the OS Red Hat Linux real-time environment, and uses essentially Power PCs as their execution platform. And the dominant user interface is MATLAB Simulink. SimPower System blocks it in their respective derivatives, their own code that they use, and in that sense they are very similar in the way they do things. Yet this came more out of the automotive industry and is now venturing more into the power systems, whereas RTDS really came out of the power systems regime as out of the HVDC Research Center at Manitoba Hydro for high voltage DC transmission systems. So they have maybe more experience and expertise in power systems. But we have both in the lab, and we use both for simulations. So let me give you some examples about controller hardware-in-the-loop projects that we had in the past. Give you a little bit.
Interchangeable?
Pardon?
Are those two simulators interchangeable?
Not interchangeable. Okay, so if you build a model in MATLAB Simulink, you cannot transfer this one-to-one to RTDS and vice versa. You would have to go through a manual translation process where you translate. They both use a graphical user interface, a similar feel to it, but different code. But there's a possibility to link them together digitally, analog. They both have analog and digital I/O, so there's no reason why you can't not use both in the same simulation. We did. We had co-simulations where the Opal RT system simulated a thermal cooling system of a ship, and we simulated the electrical system on the RTDS, and we had a co-simulation of the interaction between the electrical system and the thermal system, and demonstrated that even over long distances, that Opal RT system at the time was sitting in Alberta, Canada, and was interacting with the Opal RT with the RTDS system at Tallahassee. So controller in the loop, as I said, there's no power interface. It's mostly digital to analog connections, wires coming out of the simulator, sending analog equivalent of voltage and current over to a controller. Controller typically for power electronics is sending firing pulses for power electronic switches, and those power electronic switches then are simulated again in their turn on and turn off events in the real-time simulator. So one of the projects we had a couple of years ago was this one we did jointly with DOE and EPRI. We received a static VAR compensator controller of a static VAR compensator that utilized a 5-level topology of the switches to compensate reactive power at a wind farm in Oregon on the BPA system, and was designated to do that. So this controller, before going into the field, was sent to us to connect to a simulated wind farm and the rest of system and StatCom power stage. So we simulated all 24 switches, the power electronic switches. We simulated the wind farm in relatively high detail because we had enough of racks. We wanted to see how important it is to model a relatively high number of wind turbines versus lumping them together into either one or two machines. And there were some interesting effects out of that. And there were local capacitor banks that had to be turned on and off. And so all this was modeled on the RTDS and was sending the respective control signals that the controller needs to operate the StatCom through digital analog interfaces, so the 2 voltages, the line voltages, and the 3 currents into the controller, and it provided the firing pulses back. And we went to an entire a testing program that was jointly developed with EPRI and actually BPA and TVA at the time. And that was useful and very helpful because when you develop something like that, you're never going to catch everything, and having it on the bench is a whole lot better to deal with than in the wind farm in Oregon. This is just a slide to illustrate how accurate the model was. On the left lower side, you see a capacitor bank switching event that was actually recorded with a transient recorder. The black line is what the transient recorder produced when a capacitor bank was switching at the wind farm. When you're switching a capacitor bank, typically the voltage goes up a little bit because you provide VARs into the system. And you see the black line going up here. In about 1 second, you reach the 5%, no, it's actually only 2% increase in voltage. And the blue line is from the RTDS simulation. So the RTDS simulation very nicely captured that. If you switch in one of the smaller capacitor banks, you see that you get a smaller increase in voltage, and it did that fine. And then we just got lucky. We convinced BPA to hook up their high frequency recorders there, and we were able to capture that capacitor bank switching event even in the transient domain on the waveform. And you can see that the proper representation of the notches when the capacitor bank was switching in. You get to this level of detail in the model because you're building the model properly and going rigorously through the validation process. And with a model that is validated according to measurements like that, then you can trust that model. And I've heard many people say in the past, well, it's just modeling, it's just modeling. How can I trust this? Well, you do this, and you can trust the model, and you know what pieces you have modeled and which pieces you left off. So, of course, we use that RTDS pretty intensively for other projects. So here's an example of a test bed that we're building up for the FREEDM System Center. We have the power system part of the FREEDM system that is basically power electronic dominated systems with so-called solid state transformers. I don't want to go into any details here, but it's essentially a power electronic based interface to the grid. And the question here is, okay, I also want to have a distributed control system laying on top of that. And the way we model that is by using a cluster of 6 control boards, that processing boards that will run this real-time control operating system and the application thereof, and will interact with the simulated system through various ways of exchanging signals in digital fashion through a digital communications backbone to the controllers here. So this is, a novelty in the sense that the control algorithm that runs on this distributed control algorithm computing platform is developed under FREEDM. The rest of the system looks a little bit like a SCADA system, but this gives you a great opportunity to evaluate real-time constraints of such systems. As part of the SunGreen initiative, we have a controller, or basically a relay hardware in the loop simulation of a feeder circuit that's represented here that has an existing solar farm connected to it. It's a model based on a Jacksonville Electric Authority feeder in Jacksonville, in Florida. They're working with us on this, and the quest here is to study potential interactions between solar farms and distributed PV integration and protection. So this is just we just went through the first year of this grant, so this is just brand new. Just connected the relay to it. But we'll use this much more intensively in the next couple of years. And now I want to give you a few examples about power hardware in the loop simulation. Everything we saw so far is basically state of the art. That's the way it's done for elaborate control systems such as HVDC control system, where you dare not to afford to have any kind of testing done on the real system because it's so expensive. So this has been the state of the art for many years for control in the loop and relay kind of evaluations. This now ventures into the power on the loop. So we have a power interface between the simulator, rest of the system, and that device that's under test. And before I go into the examples, I want to share a little bit of thoughts on the importance of understanding the interfaces. If you have a circuit like that, that's a simple AC source with a 2 ohm resistor and a 1 ohm resistor in series, and you want to test this 1 ohm resistor with a virtual representation of this source here. Okay, so you would move this piece into the simulator. The rest of the system simulation runs on the real-time simulator. And you pick up that voltage, you amplify that into the real world, right? And then you connect a real resistor to it, which draws power or real current from that source. And then you feed that current back into the simulated system by means of representing it by a current source. Okay? That concept is very simple. However, if you go through this evaluation with some error in the signal, and you acknowledge the fact that you have at least one time step, if not a longer delay, between what you're sending out here and what comes back, you see that this particular case is completely unstable. Okay? If it would be the other way around, this is 1 ohm and this is 2 ohm, this is actually stable. So the interface, understanding the interface is essential to conducting real power hardware loop simulations. And here is some more results from a thesis that we published a couple of years back when we first looked at this. A circuit like this, everything looks fine. except for the fact that you incur in this particular interface, which uses 2 resistors on each side. So this is a different version of that interface that I showed before. You get an offset in the PHIL, in the power hardened loop simulation, that is not obvious right away from the get-go that you would get an offset like this in the waveform. And the waveform itself looks fine, but it's just there's DC offset. Okay, and things like that happen, and you need to really properly understand the impact of the interface to your overall power hardened loop simulation. So that's the message here, without going into further detail. An example of how useful a power hardened loop simulation is gives you this example should give you that. We simulate a very simple power system with a gas turbine generator, so this is ship power system related, and a pulse load connected to that distribution system. And on that point of common coupling, we also want to connect a variable speed drive to that. We don't have that variable speed drive in the simulation. We have it in real world. Okay, sorry, this one here. The variable speed drive is connected through this amplifier converter. So this variable speed drive sees the simulated system, and the simulated system sees the behavior, the time domain behavior of the real system. So we have this sitting in the lab, and what we did is we went through a sequence where we operate in steady state. The variable speed drive draws more or less sinusoidal currents from the grid because it's a active front end. And at this point, there is an onset of the pulse load, which reduces the frequency drastically in a couple of milliseconds, 100 milliseconds. The frequency drops because it's a gas turbine generator. You put a load on it, it drops in frequency. Everything's fine, and then the frequency picks up when you release the pulse load. The pulse is gone. And at this point, something happens. You see a transient occurring, then the current goes essentially away, and then all of a sudden we see these very distorted currents from that variable speed drive. What happened here is that at this point, the phase-locked loop of that variable speed drive couldn't keep up with the frequency increase and stopped firing the active front end, and the diode rectifier stayed on. The power electronic switches are so configured that there is a diode rectifier operation when you don't have to fire the switches. And at the end of the day, you had the diode rectifier sitting on this grid. And if you don't catch that, then under such conditions, you may end up with a diode rectifier and you don't even notice it. Okay. So this is where power hardened loop simulations can really shine. Another quick example, power hardened loop simulation of a real big machine. This is a superconducting propulsion type motor for the Navy that we had sitting in our lab a couple years back. And the quest was to make sure that this superconducting propulsion motor would operate properly and be characterized for further design of a larger machine under sea state conditions, when it drives a propeller through the water, when the ship is moving through the water and the wave action on the prop is noticeable. So we simulated that hydrodynamic model on the real-time simulator and made this motor believe that it's actually driving a prop through the water when the ship is moving and the wave action is acting on the propeller. And for a superconducting machine, that means there is additional heating in the rotor circuit, and we could characterize that, which then went into the design of the large machine. So here is a prime example of how to, power hardened loop simulation can help significantly in improving models of devices that are prototypes and need to be upscaled. Let me skip this, where this is a recent addition to our facility is a high-speed gearbox, getting the speed of the rotating machinery test bed up to 24,000 RPM. We used this most recently to test a high-speed generator for the Air Force. The megawatt scale machine that has a dedicated pulse load on it. So we emulated the pulse load using our DC version of the converter, completely controlling that experiment with the real-time simulator, and that generator now had to operate as if sitting in that application and controlling pulse and providing power to pulse loads. And the entire experiment, I think this is more important. The entire experiment was really controlled by the real-time digital simulator. We had protection on there, over speed protection, over current protection, exciter over voltage protection, and things like that. That allowed us to very precisely control the experiment and precisely protect the experiment in case something didn't, would not work with the first of a kind generator that spins at 15,000 RPM and has to provide megawatt of power into a controllable DC source sink. So that was very successful, and I think shows that you can control experiments like that with a real-time simulator. In the interest of time, I will skip this this example here, although I like it very much because we showed a nice thing, but I have to skip it. I want to go to this one here, which is an example of the utilization of the facility for terrestrial power systems, in the sense that when you have a photovoltaic converter that provides power to the grid from a solar array, the utilities are very interested in understanding how these PV converters interact with their power grid. And most of the time, the only thing they can go by is that this converter adheres to 1547 and is UL tested. And that's about the regime of understanding of dynamic behavior that the utility may have from this device. So when we showed this slide, which illustrates that we can actually connect a PV converter up to 1.5 megawatt into a simulated environment, Southern California Edison was extremely interested, and in fact shipped a 500 kW PV converter to our facility, which are now sitting in the lab connected just like this. On the one side, it is connected on the DC bus and receives current from an emulated PV array. And on the AC side, it's connected to a simulated rest of the AC power system, and we impose dynamics and transients on both sides to properly characterize the dynamic and transient behavior of this 500 kW PV inverter for the purpose of providing the model that one needs to conduct the system integration studies with more accuracy. So that project is ongoing right now, and we're looking at further, looking at anti-islanding tests and things like that. An expansion of the facility, and I'm speaking to the choir here probably, you guys have all this already, is expanding on our side. We have plans to expand the power system simulation part, which resides on the RTDS and the Opal RT, through digital interfaces to a controller network simulation in real time, which you really have spearheaded here, and hope that we have in the future have some collaboration in this. So this is an expansion plan that we have, and we'll report on this as soon as we are successful to do that. We did propose this on the DURIP, the Defense University Research Instrumentation Program, and we'll see how that goes. We're also expanding in another regime that is medium voltage DC. This is a regime particularly spearheaded by the Navy. If you think about power electronic-based distribution systems, where every device that is connected to the distribution line has essentially a power electronic interface. There's no direct connection of a classical transformer or rotating machine anymore to the distribution system. The reason for 60 Hertz AC goes away. Okay? Most of these power electronic devices have a DC bus anyway. So why not moving out these inverters and go to DC? Makes a lot of sense for ship systems. A rectifier right at the 4 or 5 or 6 generators, and then just deal with medium voltage DC. It also makes a lot of sense for offshore wind turbine collector systems. Most of them have variable speed capability and therefore have an intermediate DC bus. So right now we are embarking in procuring and installing a 5 megawatt full bidirectional DC capability that can act as an amplifier again for our RTDS simulation to conduct research and testing and evaluation, model building for DC systems. So our target is 24 kV DC, and modularly we can accommodate 5 megawatts at 24 kV and 12 kV and 6 kV. So those are the expansion plans. And I'm coming to the end of my presentation now. What I want to take home for you is that, in summary, the onset of these novel devices integrated into the grid really ask for methods like these to ensure that the models that one uses for design and planning are properly validated in a dynamic environment that can cost effectively only be achieved using power hardware loop simulation. So that's the premise here. And it also acknowledges, of course, the challenges with the real-time simulation. Many models that exist are not easily to translate into the real-time simulation world. We had many projects where, we have a MATLAB simulating model, you just translate this over to RTDS. Well, that MATLAB simulating model sometimes used 1 nanosecond time steps when it came to a switching event, and then it ran again with 500 microseconds, and then it reduced the time step again dynamically. So these variable time step solvers and methods are no good for real time. Changing and translating that over to a real-time capable model is a challenge. And as I said, the interface, the challenges with the inaccuracy and time lag of the interfaces have to be properly taken into account and accounted for. Here is a summary slide of some of the related PHL efforts elsewhere. There's some of the labs that already have some real-time power hardware loop simulation activities going on. And here are the ones in development. Clemson University is embarking on a 15 megawatt wind turbine, a generator converter testing facility. NREL is planning or is in the process of implementing a 1 megawatt converter for general purpose integration of renewable sources, and 7 megawatt of dedicated wind. The Austin Institute of Technology, which I have some connections to, obviously being from Vienna, Austria, they are also in the megawatt scale, 700 kilowatts for renewable integration. And the University of Aachen has a 5 megawatt PHL for rotating machinery and converters, very similar to what we have in the planning and implementation phase. Let's put it this way. We are as far as power hardware loop or hardware loop simulation goes, my colleague Omar Farouk at my group, he is leading a task force in IEEE now looking at real-time simulation and hardware loop simulation. So we have, if anybody's interested in that topic, would be more than happy to facilitate the contact and maybe get on board with the task force and work on this topic. Hopefully we can develop some guidelines in the future, and I'm pretty sure that if this takes off like I believe it will, there will be standards how to do this in the not too distant future, and you'll be better advised to get on the bandwagon pretty early, and you can lead these things. So conclusions, I think this is we have demonstrated that power hardware loop for electrical machinery and power electronic converters and so forth apparatus is feasible at the medium voltage level, and we are spearheading making controller hardware loop and power hardware loop really mainstream approach for model validation and experimentation in a different way that has been done in the past, and so that has a lot of application, of course, to microgrids and smart grids. And hopefully in the future we'll have more collaboration going on in this respect. So with that, I conclude my presentation and take questions.
So thank you for the great and informative presentation. This is Tim Yardley from the University of Illinois. Just a kind of more humorous question than anything else is dealing with high voltage and megawatt generation. You obviously have a fairly large power draw. How have you guys worked that into your plans in terms of running a 5 megawatt facility, for instance? while you are generating, you're also using a lot of power too. And how does that work into your research in terms of looking at things from the academic perspective of engaging in the research, but also trying to balance the costs of doing some of this work, especially when it gets to the point of, you do have controls in place to prevent harm to equipment, but sometimes you want to drive it to the edge of potential harm.
Well, let me answer the question about power draw. Look at this here. The only power we draw from the grid, and our meter is running here, right? This is our metering point, is the losses in these converters and the transformers. We're shipping power 500 kilowatt into the PV converter, and it ships 500 kilowatt back out here, goes here, and just circulates around here. So the only real power draw is when we, let me see if I can, what's this with this one here, the generator test. The gearbox that we procured has, significant losses. At full speed, you're dealing with about 9% of a 5 megawatt rating. So those are real losses that you cannot recover. But even if in this particular case, we had about 200 kilowatts of losses for the 15,000 RPM, and the 1 megawatt that we shipped through the generator, that went right back out here. It just circulates. So it's a green facility from that point of view.
Does it eventually tie back into the main grid interconnect then? Do you feed it back to the main grid? Or
no, it circulates.
Down the experiment, is it gone?
It circulates around in our own facility. So this is where the substation comes in. This is the feed from the substation. This is our transformer. So this is the metering point. We ship power through here. It's just circulating in our own facility.
This is Tom Overby. Let me ask kind of a follow-up to what Tim asked. If one were to build a lab like this from scratch, can you give us a rough idea for the capital costs involved?
Well, that's right here. Our facility currently is about $25 million invested. So that's excluding the building. We actually pay rent for that. Building was built by the Research Foundation of FSU, and we are a tenant in that building. But everything else, the high bay building, well, the building probably too, but all the machinery that you saw, the dynamometers, the variable speed drives, the distribution system, the RTDS itself, all that is roughly $25 million invested by the Department of Defense and Department of Energy.
Prosper Panumpabi. My first question is, in power hardware in the loop, you said that the interface is very, very important in the modeling. Can you give me an idea on the list of equipment we need inside that box interface? What kind of equipment you have inside?
Well, okay, I can show you. Okay, so this is, to me, the interface consists of the actual power amplifier, and then the algorithm that how you implement the feedback, the feedback from the real world back into the simulation. Those are two pieces. The actual physical interface in this case is a back-to-back converter system. And behind this, in this cabinet, there is a bunch of IGBTs, integrated gate bipolar transistors, that switch at 2 kilohertz and rectify power from the grid into DC. And then on this cabinet here, there is an inverter stage that, by reference from the RTDS, modulates the output such that it recreates that waveform. And now, all this, of course, in a high-power device like that, you have control systems and protection and all sorts of things. Currently, we are facing roughly 300 microsecond delays when we send a signal until it actually shows up at the output. Okay, so that bandwidth has to be taken with a grain of salt, because it of course is a steady-state frequency characteristic and not necessarily a transient. It doesn't take into account the delay time that you incur from before sending a change in voltage to when you get it at the output.
Thank you. My second question is, I did my thesis on the degradation of the wind farm. I saw that you had this experiment where you did the validation in the RTDS using Area 3 wind tower, and coming up with the result that it was close to the real simulation. Did you try as well also to do inside the RTDS the aggregation of
Yes.
all the Area 3 wind tower in one?
Yes.
What kind of result did you get?
Well, so we started out, we aimed at modeling as many of the generators we could using our 14 racks, and we were able to get 36 individual turbines onto the 12 racks. Now the turbines have included the wind turbine itself, the gear system, the fixed speed induction generator, which had to be modeled with 2 generator models because they are actually pole switched machines, 4 to 6 pole, and there was no pole switchable machine model in RTDS, so we used 2 to switch from one machine model to another one. We had the soft starter, the local cap bang, and the step-up transformer. All that was modeled in the RTDS. That's why you end up with 36. So we said, okay, that's roughly half. Every second machine, 2 machines into one was lumped. And when we did that, and we exposed the wind farm to a non-uniform wind speed profile, we could clearly see that the reactive power draw of this 36 equivalent representation was significantly lower than the single machine equivalent. And that's simply because the reactive power draw from an induction machine is non-linear dependent upon the real power draw. So the machines that had more wind speed and therefore more power injection were significantly higher drawing reactive power than the ones with the lower, and that showed up in that detailed simulation. Now you can use that information to reduce the model to say a 2 machine equivalent, right? And we did that also, and working with Southern California Edison for many of their wind farms, we are in the process of doing that.
Yeah, my last question, if I can guess, maybe it's just, I'm guessing, if you might be a power electronic, background, how do you make sure to interact with, all those people involved, because you have to work on the power system or the control on, how do you make sure that all the 100 people, working, they work together, for the same outcome, because you have to work with different, people.
As far as the research group goes, or
yeah.
Well, that is a challenge. I acknowledge that. In my group, I try to ensure we have that versatility, so we can cover the bases. But making sure that that research groups have working on a common research project, and you get the diversity of the experts in there. We have in FREEDM, for example, we have that. We have power system folks, we have power electronic folks, and device folks, and control network folks. So.
This is Kevin Jin from University of Illinois. You mentioned that you had a plan to connect your power testbed to the network simulator, and I'm wondering, both conceptually and technically, what are the challenges you foresee to connect these 2 types of different simulators, different testbeds?
You're referring to this expansion thing here? Oh, come on. This one here?
Right.
Okay. Well, it's a matter of, if you utilize standard protocols that the utility community uses and RTDS has provided interfaces for, such as DNP, Modbus, 6150, then it's a matter of getting the respective number of I/O cards for the RTDS, and then having the counterpart in the real-time network simulator. We also experiment with customized protocols that we develop on dedicated FPGA platforms that are seamlessly tying into the RTDS. So I think the interface here is one of the major challenges that one may face, and then of course the expertise in this regime, which clearly you guys have the head start on that. Okay. Yeah. Thank you.
Again, thank you all for coming. So hopefully we'll continue with discussions with your center, and you know, some of the people who talked during the day were you know, some ideas we might pursue in common. But anyway, thanks, Mischa, for coming out. A very interesting talk.
Thank you very much. Thanks for having me.